Hi guys, your Friendtor Gopika is here, and in this video we will discuss the tangent theorem, the first theorem of the chapter circle, tangent theorem, and its converse, okay, along with proofs of both the theorems we will discuss in this particular video. In the last video we already discussed all the recall part, so without wasting time, let's get started. Okay, in the previous video we discussed or we recalled all those concepts related to circle that you have learned in the previous standards or in the previous chapter, and we also discussed some new things regarding number of circles passing through 1 point, 2 points and 3 collinear or 3 non-collinear points. Okay, such 4 cases also we discussed. Now let's start with the actual chapter, that is tangent and secant. So first we will see the definition of tangent and secant. So if you see in the first figure, first let me choose the point. Okay, in the first figure there is not even a single point common to this circle with center A and line L. Okay, they are cast apart and they are not connected, or they don't have any even a single point in common. But if you see the second diagram, here you have a circle with center B and a line M, and there is one single point which is common to both the circle as well as the line. Okay, so if you have a line such that it touches the circle just at one single point, then that line is called as tangent of the circle. Okay, and this point P where it touches the circle is called as point of contact. Okay, so a line which touches the circle at single point is called tangent, and the point at which it touches the circle, that single point, is called as point of contact. Now in the third figure, if you see, 2 points Q and R are common to both the line L and the circle with center C. So this third circle, here the center is C and this line is passing, or it is touching the circle at 2 different points. One is at Q and another is at R. Okay, so it is intersecting at 2 points. Now such a line wherein it touches the circle at 2 points, then it is called as a secant of the circle. Okay, it's just like an extended chord. Chord is a segment, and here we are talking about a line. That's it. Okay, so these are the definitions of tangent and secant. Now next, here is an activity, and in this activity we will conclude a very important property or theorem of tangent and circle. Okay, so here draw a sufficiently large circle with center O, radius OP, and draw a line AB perpendicular to segment OP. Okay, so first draw a line AB perpendicular to OP. It intersects the circles at circle at 2 points, that is point A and B. Okay, now imagine that this line is sliding downwards. Now from here, from the first position, it reaches the second position. Okay, and it is sliding in a straight line. That means it is parallel to the original position it is sliding, and slowly it will come down and down and down. So once it is going one step, then A is shifted from here to here and B is shifted from here to here. Then when it goes to the third step, A is shifted down and B is also shifted down. Then the fourth step, again A comes down and B also comes down. Then when it reaches the tip of the circle, or when it reaches that end, then A and B merges to one single point P. Okay, so we began from here, and here we had drawn a line which is perpendicular to the radius OP, and we just slided it downwards and we reached here. Okay, now this line is like a tangent. Okay, and we were sliding it in a straight line, or we were sliding it parallel to the original position. Okay, that means this tangent is perpendicular to the radii. Okay, since we were sliding a perpendicular line towards the end, this tangent should also be perpendicular to the radii. Okay, so this is what this is that important property of the tangent. Okay, so the tangent at any point of a circle is perpendicular to the radius at the point of contact. Okay, so whenever you have a tangent and if you join the center to the point of contact, then that radius which is formed is perpendicular to the tangent. That is what tangent theorem says. So this property is known as tangent theorem. And now let's read the statement. The tangent, so the statement says, the tangent at any point of a circle is perpendicular to the radius at the point of contact. Okay, this is the statement. Now we can prove this indirectly. Indirect proof means we will assume that L is not perpendicular. Okay, we'll assume that whatever we need to prove, we will assume that it is not true, or we will assume its negation, and then we will arrive at some contradiction. Okay, that is how we prove. That is what we mean by indirect proof. Okay, starting with the negation of the actual to prove statement and then arriving at a contradiction. So the given part over here is line L is a tangent to the circle with center O at the point of contact A. So if you see this diagram, you have a circle with center O, L is the tangent and point of contact is A. To prove that line L is perpendicular to radius OA. So in indirect proof, our first assumption should be line L is not perpendicular to segment A. We will start with say the assumption that line L, suppose line L is not perpendicular to segment A. Okay, so if line L is not perpendicular to segment A, then let's draw or let's construct a segment OB such that it is perpendicular to line L, and of course B is not same as A. Next, now take a point C on line. So first what you do, you assume that OA is not perpendicular to line L, then construct a segment OB such that it is perpendicular to L. Next, construct OC such that BC and BA are of same length measures. Okay, so if A is below over here, then at the same distance from B, construct C and join OC. Okay, now what we will do is these two triangles, we will deal with these two triangles and find something a relation in between them, and then we will use that fact to prove that OC and OA are same. Okay, so for that we'll go to the next step. Now in triangle OBC and OBA, so once you have this diagram, then we consider these two triangles OBC and triangle OBA. Okay, so here BC is equal to segment BA, segment BC is equal to segment BA, or they are congruent by construction itself. Next, we know that angle OBC is equal to angle or congruent to angle OBA. Both are 90-degree angles. Why? Since OB is constructed in a way or drawn in a way that it is perpendicular to line L, so it is forming 90-degree from both the sides. Now, OB is common segment as well for both the triangles. So segment OB is congruent to segment OB, and the reason is common side. Hence, these two triangles are congruent by SAS test. Two corresponding sides are congruent and one corresponding angles, one pair of corresponding angles are congruent. Hence by SAS test, these two triangles are congruent. If these two triangles are congruent, that means the corresponding sides are also congruent. So OC is equal to OA. Now what was OA from the beginning? OA was the radius, correct? If OC and OA are same, then OC also should be the radius, correct? If OA is also radius and OC is also radius and both of them are touching, that is C also is a point from line L, A is also a point from line L, and if both of them OC and OA are radius, that means C also is lying on the circle, A is also lying on the circle. Okay, that means this line L is intersecting the circle at two different points. Okay, so this is against the definition of tangent. You know that a tangent can touch the circle only at one single point, that is if it is touching it A, then it cannot touch in any other point on the line. So here if the line intersects the circle at 2 points, then it is not a tangent. So but since line L is a tangent, it intersects the circle in only one point. So our assumption that line L is not perpendicular to radius OA is wrong. Okay, so our assumption that line L is not perpendicular to OA is wrong, because when we assumed that, we arrived at the we concluded that there are 2 points on the line which lies on the circle and which is contradictory to the definition of the tangent. That means our assumption is wrong, and hence line L is perpendicular to radius OA. Okay, so this proof actually is not, I think this won't come in the exam, or it's not part of as such the syllabus, but the statement is really important, and proof is given for you in the for information part. Okay, for more information. So I think at least once, if you don't see the proof, then it's difficult to actually understand what the theorem want to say. Okay, though the statement is important, when you go through the proof, the statement just registers in your mind, and it's easy for you to remember the statement later if you have seen the proof, and it is convincing as well. Okay, when you just read the statement and when you use it in problems, then you always have a doubt in your mind that why is this true and why this is happening, all that stuff. Once you see the proof, then you are convinced and satisfied that this statement is true, and we can use it in the problems too, or to solve the problems, or in any other theorem wherever we need this concept, we can use it there. So at least once you should see the proof. That is what I feel. And yeah, that's it. Okay, so now let's see converse of tangent theorem. Okay, so here the statement says a line perpendicular to a radius at its point of contact on the circle is a tangent to the circle. Okay, so a line perpendicular to a radius at its point on the circle is a tangent to the circle. So if you have if you choose one, if you make one radius, and if you draw a line such that the line is perpendicular to the radius, then the line formed will be a tangent to the circle. That is what converse of tangent theorem says. So the given part is M is the center of a circle, segment Mn is the radius. So in this particular circle, M is the center, Mn is the radius. Line L is perpendicular to segment Mn at point N. Okay, so these three things we know. What we need to prove is line L is tangent to the circle. So for proof, we will start. Take any point P other than N on the line L and draw segment MP. So other than N, take some point P on the line L and join MP. Okay, now in this triangle MNP, if you see, angle MNP is 90 degree, or angle N is right angle. Why? Since Mn is perpendicular to the line, angle MNP is a right angle, or angle N is a right angle. That means segment MP is hypotenuse. So here segment MP is greater than segment MN. Why? Because hypotenuse is the longest side, or is the largest side of a right angle triangle, and hence MP is greater than Mn. Okay, now as Mn is the radius and point P can't be on the circle. Why? If Mn is the radius and MP is greater than Mn, that means point P is outside the circle. Okay, radius means the point N is on the circle, and greater than Mn if you have a segment, that means the point P is going outside the circle. Okay, so point P can't be on the circle. So except N, if you choose any other point on the line L, then that if you choose Q over here, then MQ will be greater than Mn by the same reason, and again Q will be outside the circle. So any other point on the line L other than N, okay, except point N, any other point on the line will never lie on the circle. Okay, So line L intersects the circle at only one single point, that is N, and hence line L is a tangent to the circle, clearly by the definition of tangent. Okay, so that's it with the converse of tangent theorem. Okay, so that's all for today's video. Please like the video and share it with your friends. Please subscribe the Friendtor channel, and you can also follow us on Instagram. And if you have any doubts regarding any lectures that we you see in this channel, or you have any doubts regarding mathematics, then please write in the comment section, or also you can DM us on Instagram. We will respond as soon as possible. So thank you.